Hello, students. Mr. Sanger coming at you from the chem storeroom. Got the safety shower all set up just in case this screencast gets a little nutty. So this is meant to be watched after having completed the lab where you drop different types of liquids onto a penny. So at this point, hopefully you have data, and now it's time to get our post-lab. So let's talk about what we do with that data. So the first thing is you need to graph it. Now, the question that you need to decide every time you're asked to graph anything, which will be often both in this class and on the actual AP test, is do I use a line graph or a bar graph? So to understand that, let's look at two sets of data. It does matter, by the way, which one of these two graphs you use. So there is a right and wrong answer for which type of graph. So in data set A, I'm going to look at 4 different kids, and I'm just going to measure their height, and I just want to compare their heights to one another. Which type of graph should we use for that? Pause and think. And data set B, what I'm going to do is I'm going to track the growth of one child. So at age 1, this is their height. Shame on me for not saying inches. Ooh, I gotta fix that. For year 2, this is their height, year 3, etc. And so which type of graph would I use to graph that data? Have you committed? Here are the answers. In this first example, note that we are comparing values. So we're comparing child 1 to child 2 to child 3 to child 4. They're all kind of independent. It doesn't really matter what order I put these in. So if I put child 2 first, it doesn't change the meaning of the data in any way. So in this kind of case where you're comparing values, you use a bar graph. Okay. Now note that I have the independent variable, the children, and the dependent variable properly labeled, independent on the x, dependent on the y, and then note that I've included my units as well where appropriate. Note also that my title has both the dependent variable and the independent variable in it. So that's really important. In the second set of data, note that we are showing a trend. We're showing a change over time. So if I rearrange these values and put like year 2 in the beginning, that changes the meaning of the data. That doesn't really make any sense. I can't do that. So in this instance, where you're showing change over time or a trend of some sort, that's where you use a line graph. And notice again, I've got my dependent variable and independent variable labeled on the y and x axes respectively, and the units as well. The format is important. So, you can read that little comic here. And I know since you were probably in like 5th grade, teachers have been harping on you to label your axes. Every single AP exam, you are going to be asked to graph something. And every year they talk about how so many kids lost points because they didn't label their axes and they didn't include their units. So get in the habit, make life easy for all involved, get in the habit of labeling that those axes. And if you look at the rubric for how we're going to score these, you'll notice that labeling your axes is on that rubric. So don't lose points on every single lab because you forget to label your axes. That's really important. Okay. So at this point, you may want to pause, turn to your group, and then reflect on the data you just collected for the penny lab. So what type of graph should you use for the data you collected? What should go on each axis? And then again, what should always be included on that graph? Like always. And I'll give you a hint, label your axes with units. Okay, so at this point, I'm not going to tell you the answers to that. That's for you to discuss. But once you have that data and you've graphed it, now we need to interpret it. And we're going to employ, this is new for I think most of you, we're going to deploy the tools of statistics to do this. So there's a couple issues that sort of come to light. And in earlier science classes, we're kind of like, we won't worry about this too much. But here, no, it's time to start worrying about it. So issue number 1, do you think that there's a significant difference in each of the data sets below? So look at these data. Let's suppose you collected a number of drops on penny and you found that you got 10 on water and 10 drops of isopropyl alcohol to fit on a penny. Is there a difference between those two? And I think everyone in the world would say, no, there is not. 10 is the same as 10, so there's clearly not a difference. How about this data set, though? So it turns out you can get 18 drops on the penny with distilled water, but you can only get 2 drops with isopropyl alcohol. Is that different? And again, I think most people are like, well, yeah, that's pretty different, right? 18 versus 2, that's clearly pretty different. Okay, so there's difference. Something significant seems to be happening. How about this one though? Let's suppose you get 12 drops on the penny for distilled water, but only 8 for isopropyl alcohol. Is that different? And this is where it becomes kind of a gray area. You know, it's kind of like when you flip a coin 10 times. You should get 5 and 5, but you might get 6 and 4. You might get 7 and 3. So at what point do we actually say there is a difference? So how do we know, the way we'd phrase that in this class is, how do we know if the differences between our treatments are statistically significant? Issue number 2, when you added the drops, you did multiple trials, and the question is, did you get the same number of drops each time for the same substance? My guess is no, you did not. So here we have some sample data, and we can see that, you know, trial 1, we got 88 drops for water, 85, 90, 94. Like, they're different every time. And that's to be expected, right? Because it's drops of water on a penny. And yet it does raise a question, like, we should probably address that. Like, how do we represent the spread of that data? So how do we know, our 2 issues, how do we know if the differences between our treatments are statistically significant? And how do we represent the spread of the data? Well, it turns out that the answer to both questions can lie in these things called error bars, and they look like letter I's that sit atop bar graphs. So let's talk about how we work with error bars. The error bars represent a statistical property called the standard error of the mean, specifically 2 times the standard error of the mean. We're going to talk more about that standard error of the mean in the screencast, but for now, that's just what they are. It's 2 times this value. And that represents the spread of the data. The error bars also indicate if the differences between trials are statistically significant. If those error bars overlap one another between 2 trials, that tells you that the spread of the data is kind of overlapping, and therefore the differences are not statistically significant. If there's no overlap, then that tells you that the spread of the data doesn't overlap, and therefore the differences are not. The differences are statistically significant. So take a moment. In the trials below, which bar has the broadest range of data and which bar has the narrowest? So kind of take a look at these different error bars and which do you think has the widest spread of data and what has the narrowest spread of data? And then 2, assume that dark green is a control group. Is there a statistically significant difference between the light green and yellow trials with compared to that control group? Okay, so pause, think about those 2 questions. And here's the answer. So the trial that has the broadest range of data would absolutely be this yellow one right here, because that has the widest error bars. So that's a larger spread. The narrowest is this light green, very narrow spread. Okay, so all of these trials were very close together. Assume dark green is the control. Is there a difference? Well, in this group right here, the dark green versus the light green, you can tell that there's no overlap between these error bars, so we would say there is a statistically significant difference between the light green and the dark green treatments. Yellow, on the other hand, does overlap, so we would say there is no statistically significant difference between the dark green values and the yellow. In other words, the green and the yellow are the same from a statistical point of view. Over here, the dark green, light green, actually look close. There's no overlap, so that's statistically significant. That's different. And the yellow and the dark green do overlap, so there's no statistically significant difference. Okay, so how do we then calculate those error bars? Well, to do that, we need 2 quantities called standard deviation and standard error. There's a little video that goes through this, and so if you're still confused when I'm done, I guess I'd recommend you going into the slides and clicking that. So standard deviation is a measure of the spread of the data, so how much variation there is. So this is a screenshot from that video I mentioned, and in this video, they did a trial, or they did 5 trials where they just measured the weight of a mouse, of different mice, and they plotted those values. So 5 different mice, 5 different weights. The mean, or average, is here, and the standard deviation is this spread of the data. To get the standard error, what you do is you repeat that experiment multiple times. So now you're going to measure 5 different mice once, 5 different mice a second time, 5 different mice a third, 5 different mice a fourth, and each time you're going to get these different means. So once we've done that, now we have a mean of the means, and we have a spread of data for the means. That is the standard error. So the standard deviation of the means is the standard error. And what's weird is even if you only do one trial, so even if you only did that red trial, you can still actually calculate the standard error mathematically. And that's kind of weird. So the standard error is really important because it's a measure of precision. It tells you how close is your measured mean to the mean you would obtain if you repeated this experiment dozens of times. So that standard error is critical because, again, it tells us, like, if our data is like this, that means, okay, we really are measuring this well and have a really tight hold on our data. If we get this, then it's like, okay, our data is kind of all over the place and there's a huge spread, and so therefore our values are probably not quite as reliable as you might want to think. So that standard error is simply a way of quantifying that. Okay, in this class, the error bars will always be equal to 2 times the standard error of the mean. Okay, so you basically take that value, you multiply it by 2, and then you go above the mean and below the mean with that value. 95% of the time, the actual mean, whatever the real value is, will fall within 2 standard errors of the mean. And you can kind of see on this bar graph, this is kind of your range of data. Here's your mean, your average. That's your mean. And so then 1 standard deviation incorporates 68.3% of the data. So 1 standard deviation only captures about 68% of the data. 2 standard deviations capture about 95% of the data, and 3 standard deviations capture about 99.7% of the data. So that means if you did this experiment or you made that measurement 100 times, 95 of those times, the value will be within 2 standard deviations of the mean. Okay, so and it's true no matter how spread out the data is. So if you have a relatively small standard deviation or relatively large, 95% of the time, the data will fall, the actual mean will fall within 2 standard deviations of that mean. So I'm going to pause at this point, and then we're going to continue with part 2. And in part 2, we're going to talk about how we actually calculate these things mathematically.